About a year and a half ago, I was reading Popular Science, and I read this article about this company called Quicklaunch, which had this incredible launch system described here. And it was very exciting, and I had John Hunter. I found out he's just in the area. I was very excited. He's right in the area where we live. So I had him come and give a talk at our local Mars Society club meeting called Space Up. And it was very well received. And so since then, we got a Facebook page called Quicklaunch. We're trying to get some funding in phase and so forth. But this system, if you can imagine a long straight tube with a pressurized hydrogen valve opening up and have a projectile that surfed that hydrogen wave up to the end of the tube, how fast would that be going at the end of the tube? Well, we're talking about like Mach 33, a tremendous amount of energy and a tremendous amount of speed imparted to that projectile as it goes down the tube. So you're at the end of the tube. I mean, this is exciting stuff. You know, a sonic boom, a huge flash of light, and a meteor going that way, right? And so this is like, it's believable, it's doable. The gun exists. It's in San Diego right now. You can go see it if you want to. It's not. I mean, it's in pieces. It's in storage. But there are systems like this. I guess Arnold, Texas, there's one that shoots things that are going this fast. So this is a way to get things in space at a much cheaper cost than rocket launch. It's doable. It's not like some crazy space elevator that's tens of thousands of years away from us. So let's give a very warm Mars Society welcome to Dr. John Hunter.
Thank you, Eric. That was too kind. Yeah, Eric's enthusiasm is what the Mars Society really needs. I made a drunken comments a few days ago that we need to get better attitude here. I think it's all true. You have a positive attitude. Okay, now, how do I go forward in this thing? Do I just do this little, this guy here? Okay, so I go back and forth. Okay, so, yeah, this picture here, the spin-off of it was in Popular Science about a year ago. A little bit, I'll give you 30 seconds on myself. I used to be a particle physicist when I was a kid. Went to Lawrence Livermore. I was hired to build magnetic guns. I got sidetracked at a cocktail party into hydrogen gas guns by accident. I didn't know they existed. Someone just mentioned them offhand. I looked at the data points, and in 1989, I saw that it was a done deal because hydrogen had all the world records for velocities. And I'd been hired to build magnetic gizmos, you know, because I was a particle guy. I knew about magnetic fields. I was hired to build those things for Livermore to launch stuff into space. But the gas guns had all the world records, and it was apparently very easy to do. So at the age of, I guess it was about 28 or 29 years old, I switched from being a theoretical physicist to being a guy who built stuff. I was just very tired of lots of equations and no results. So I started building these gizmos. First gas gun I built was this big, and it got to within 1% of my code predictions, which was a shocker because in particle physics, you're never within a factor of 2 to this day. Okay, so string theory is even worse than that. And so I was just amazed. It was very, very, it was a good feeling to actually have a tangible gizmo that works and is so predictable. And then, of course, the upside is these things can launch stuff into space because the speeds of hydrogen are matched to orbital speeds by coincidence. So what you have here is a total natural. To me, it was a nanosecond realization or femtosecond or whatever you guys call that. But it was a very short amount of time I realized that this was a solution. And of course, it turns out Jules Verne was way ahead of me. He oversaw this in 1880, whatever it was. So I wasn't the first guy. But we were among the first to realize you use hydrogen as opposed to gunpowder. Let's see here. Next one, huh? Okay, so long story short, a couple years later, I built 2 systems. I used each system. The first one to bootstrap the next system. I used this little guy to sell the 10-foot system that got 8 kilometers per second. I used that. I built that and shot that in 3 months, 2 months. And then I used that second system to bootstrap and get IRAD money to build Super Harp, which was the world's biggest gun of any sort. It was 425 feet long, I think, plus or minus 20 feet. And it's there on the left. And so it was so long you had to ride a bicycle around it because otherwise you have to spend 5 minutes going from point A to point B. It was a weird exotic gun. It was in Smithsonian magazine and stuff, but it was L-shaped, and it was a classic 2-stage hydrogen gun. And we did it very, very affordably. And the lesson here is not the physics, because I'm like an average physicist, but it's about the psychology. Because if you use aerospace materials and aerospace contractors and congressmen and the usual 9 yards, you're going to get incredibly bad prices. You're going to get prices that will kill any project. That steel was in Houston. I had the world's best engineer, Red Reinecker, we flew to Houston. We found this oil well steel called Z199, which instead of being 10 or 20 bucks a pound, like most of the weapons steel was, it was about 4 bucks a pound finished. So they would actually do these forgings at Cameron Forge, extrude it out, machine it to our super duper tolerances, test them for us, and ship it to us FOB Livermore for $4.40. That was the big breakthrough. Let's see here. Okay, oh, so this is a fired a shot. This is Adak Island. I was on Adak just before 9/11. We were getting ready to start this company just before, 4 days before 9/11, and of course I took this picture. We superimposed a JPEG of what this thing would look like there on the island. Adak is a very nice island in the middle of the Aleutian Islands. But of course 9/11 happened, and I got wrapped around the Iraq axle for about 4 or 5 years. And so, which is as it should be. I mean, that's what you should do, is switch gears and pursue the other project. It was a more important project. And then subsequently, so back in 2010 or so, we got back involved and pursued the big aquatic version. Now, this was in Popular Science about a year ago. It explains it very well, actually. This is the aquatic version. There's a land-based version, but the aquatic version is very nice because this version can basically aim different directions. You're not fixed to one inclination. You know, one of the big hits on these land-based guys is they're only launching to one inclination. So if you're at 28.5 degrees, you launch basically once a day, unless you've got multiple depots. Whereas if you have one that could launch for multiple customers, you could launch, say, do a shot every hour or two to an equatorial depot or set of equatorial depots, and then 2 days later start launching sun synchronous. You just turn this thing around. It's in the water so you can steer it around. Now how it works is you have hot hydrogen here. We have a heat exchanger using natural gas, which of course is the greenest hydrocarbon you can use, so everyone's happy in the green community. It heats the hydrogen up. We have a release valve. We have the vehicle ahead of it. And these little things here, these look like flapjacks or pancakes, like we had at the Waffle House this morning. And they sort of the recoil of the system. So when the system fires, when this thing releases, these little pancakes go backward against the water, using the water as a muzzle brake, or basically as a recoil brake. It goes down this long tube. These are tensile members, elements, and these are donuts to hold it in location. They also provide some buoyancy. And the last couple nice features is it's neutrally buoyant, so you don't have this tube flopping all over and acting like spaghetti in the water. It's neutrally buoyant, so it basically sort of stays where it is, and you don't have the drift and sag. And the last thing that's sort of cute is we have a muffler on the end where we capture 99.9% of the hydrogen each shot. And we've already done this stuff. In other words, I've built systems that have caught 97% on the second shot. So we know we can build the mufflers, we know we can build the heat exchangers, etc. I've never built a composite system, so you know there's a few things left to do. Okay, now here's a very important metric. I was not initially a Mars aficionado, but I looked at this stuff recently. And I looked at 2 studies that were by smart people. One was von Braun, and then there was a Boeing study using nuclear rockets back in the 60s. I wanted to find out how many millions of pounds of propellant you need to send a person to Mars, and how many for the moon. And for the Mars, I had to average these 2 studies, and the answer is 1 million pounds. So you need 1 million pounds of propellant to send a single astronaut. This is from low Earth orbit to Mars, and then get him back to Earth safely. Okay, it's 1 million pounds. It's a very convenient metric. It turns out the one for the moon is almost exactly 1/10. You need 100,000 pounds for the moon and back. So now, project yourself forward. Okay, you want to send a bunch of jockeys and you know, or one person, or would you rather send 10 people and have actually sort of a civilized transport? And the answer is you really want to send at least a couple handfuls of people, or else it's going to be there's going to be problems. So I would say you'd send 10 people. 10 people is going to cost you, if you at the current rate of 5,000 a pound, it's going to cost you $5 billion per person. So it's $50 billion for propellant alone. That's what it's going to cost you right now, $50 billion for propellant. Game over, right? You guys know the NASA budget, the ESA's budget, you know what their legacies are. So if you bring those costs down a factor of 10, which is what we can do, we believe we can do this, or better, then it comes down, the total cost is $5 billion for the propellant, for 10. Okay, I'm going to zip through this here. Okay, here's the Mars metric. You can see what happens. We actually have data on Mars. It's 122,000 per person. And here's a little curve for scientific types, and it shows you that if you're down here, this is called dry mass fraction, but the bottom line is with a single stage RP1 system, you're at 22% payload fraction. As you know, most rockets are 3 to 4% on a really good day. And you know, the trick is we amortize. These other systems, these rocket systems, do not get to reuse significant parts. And I hope that they can. I mean, it'd be nice if Elon Musk could reuse some parts of his, but I consider it sort of unlikely because I've shot things up to Mach 20 roughly. A lot of stuff around Mach 9 for scramjets for the Air Force. We never recovered anything. It was all vaporized in the sand pit above Mach 4. So I'm not optimistic that guys are going to recover rocket stages that are leaving disassembly at about 3 kilometers per second, which is like Mach 12 or Mach 13. Conventional rocket costs, this would be like a Delta IV Heavy, 5,000 a pound. And I believe that Elon probably is really truly at 2,000 a pound. I think he's telling the truth. And he may get down to 1,000, but because of this little trick here, we reuse the gun. In other words, it's not a one-shot pony. We reuse this system many, many thousands of times. We pull the liners and replace the liners periodically because parts of the gun are going to wear. But as you noticed, this is a classic rocket versus gun curve. The rockets always win if you only do one shot. But the guns win at some crossover point, which happens to be, in this case, it's about 20 tons per year. So the gun starts to win and gets amortized. So now you're down here, you're looking at purely the single-stage vehicle cost. Now this is something my designer just whipped up. I thought it was sort of cute because we have these pictures for the Earth. They've been in some magazines and stuff, but this is, I superposed it on Mars. So that's what our depot would look like. And this is not your conventional depot that the rather large aerospace companies are proposing because they usually have sort of self-fulfilling depots that could be very large and you need 18 rockets to launch the depot even when it's empty, okay? So I said, no, we don't want to do that. Let's just launch a manifold. We will attach our systems to the manifold. The manifold weighs almost nothing. And then the guy comes in with a credit card and clicks it in and you deposit the propellant. Now you notice this does not have a giant solar heat shield, etc., like a lot of the guys want because they want to do cryo. And I think cryo is fine, but this is a very generic system. Looks like it would be for a room temperature type liquid propellant. Okay, there's a picture of the one you saw a minute ago. I think you guys understand that now. This is what it looks like coming out of the barrel. And that's my rendition of it flying through the sky backwards. Looks like a comet going backwards. And there it is with the moon in the background. You're at about 100 kilometers. The aeroshell now falls. You blow the aeroshell off. This is the single-stage motor. And by coincidence, since it's carrying rocket propellant as one of its payloads, we're only looking at putting propellant up. We don't want to launch people, electronics, anything fragile. We could launch electronics, but we're not going to do it. So we promise we're just going to launch propellant. And the good news is that's 95% of the market. So we only want 95% of the market. I'm not a greedy guy. And of course, this is artist rendition thing flying over a beautiful picture taken by NASA. And there it is coming in. And now let's see if this works. I suspect that the video stuff is not going to work. But that's okay. We'll get to that later. And here's a sequence. We've got a, let's see here, TV interview. They did some great interviews, but I'm not sure if they'll come on this little computer. So I'm just going to go directly to the quotes. You've seen these quotes before, right? Everyone now realizes you've got to have depots in orbit. Mike Griffin. Mike actually gave me $500,000 back in 1989, back when he was at SDIO. We used it for Super Hard, so he liked the project back in those days. And of course, the Augustine report, those guys figured out that you need to have things cheaper, but that's not rocket science, right? Barack Obama, as being a regular politician, actually intuitively understands this, that you've got to do something different. It's not working, and so this is something different. And it's one of the few things I've looked at that looks like it's got a super duper chance of happening. Of course, the other thing I think is Elon Musk, which is, if I was you guys, I'd invest in his company, but the other thing I'd invest in my company. Okay, this is something we always get questions, can you G-harden electronics? Because that's, some people would like us to launch satellites. The answer is yes. And it's just sort of this classic. I hired 3 or 4 consultants. Some of the guys were extremely expensive guys. And they were complaining to me, oh no, you need to use high salt 9309 and it's going to look like a brick, blah, blah, blah. And then I talked to an old weapons guy in the East Coast. He says, no, John, this is pathetically easy. He says, you just go to Walmart. Don't get the good stuff. Go to Walmart. Buy the cheap epoxy. And you look at the parts on any kind of hard on-surface mount electronics. There's always going to be some relays and some transformers. That'll be a little bit heavy, so you put a little fillet of epoxy around those parts. The other parts, you take a cocaine dealer scale, okay, which I did actually, Take a cocaine eater scale, and you weigh all those little tiny parts. And you know the Botter-Son strength is 2 ksi. So then you can do F equals MA, and you can figure out what the safety factor is. And lo and behold, at 3,000 Gs, it's over 200 for things in your cell phone. It's 200. The things that'll break, and I've done this, I've shot cell phones out of guns, so one of the few people that's done that.
Did they survive?
A lot of satisfaction, actually. It was quite fun. So they survived. They survived, but I had to harden the transformers and relays and the LCDs. Those are the only parts that got to harden on these things. But we took all these off-the-shelf parts. This was a GPS. These are photovoltaics. Dan Golden, who was the head of NASA at the time, and I ran into Dan. He said he liked this stuff. He would have a hard time G-hardening photovoltaics. None of them failed. We just did it, bam, like that. Okay. So these were amorphous silicon. We wrapped around the thing a couple of times, shot it out of the gun repeatedly, 22 tests. I had a TV camera in here. This was done without prints. Before we had SolidWorks and prints and all this stuff, we just did it. Went to National Test Systems and built this thing in a few weeks and shot it out of the gun. I returned the drug as scales to the cocaine dealer. I was good. Okay, now a little background. Okay, I didn't invent hydrogen gas guns. They were invented in 1945 or 44. And the trick is they have a very low molecular weight. The figure of merit for any kind of gun that uses gas is the sound speed. Because if the molecular weight is only 2 versus 22 for gunpowder, you basically have about 3 or 4 times higher sound speed. It goes like the square root. So hydrogen gas guns are at least 3 or 4 times faster than any powder gun. In fact, that's why they have the world record, which is 11.2 kilometers per second. That was set by NASA in 1966. I built gas guns, got 8 kilometers per second routinely. It's no big deal. And then, of course, you have electric guns. I was hired to build electric guns, so I know all about them. They spent almost $500 million, probably more than that by now, on rail guns, pulsed induction guns, coil guns, reconnection guns, quench guns. They kept renaming them after every failure. Okay? Pretty smart. But basically, they never got over 5.5 kilometers per second. Although on one occasion, they took a gas gun and injected at 8 kilometers per second. They got it to 8.2, and they declared victory. And I said, "Well, are you sure, Ron, that you didn't actually inject at 8.4 and subtract off 0.2? I think that may have happened. Now, this is the thing. Hydrogen gas guns are suited to orbital because orbital is 7.6, right? 500 kilometers. That's a very vanilla speed for hydrogen gas guns. We're not trying to set world records for speed. And of course, I mentioned we've already captured 97% of the hydrogen, so we'll recycle the hydrogen per shot. Let's see here. And this is a picture of the gun, the business end of the gun back in the 90s when there was a Livermore. My favorite giant gun. Little picture of the construction phase. And there's the guys at National Force. These guys were a great company down in Pennsylvania that did the hardest part of the gun. It was L-shaped, so I had this massive piece of steel at the turning location. And we used the world's best core. It was AF-14 tin for the core of that steel part. And then we shrink-fitted 3 other pieces around it. And these guys knew what they were doing. They would heat up the outer part, and like 100 degrees Fahrenheit above the other one. And then, of course, things expand, right? And they would put it inside, and 30 minutes later, it would lock up, and then repeat the process. Here's Lou and Paul Heston. These guys were mechanical guys that ran this thing. You can see we had a bunch of overhead gear because it was not automated. This was a giant zip gun, so everything weighed about a ton or two. Those pistons all weighed at least a ton. And so we had 100 tons on the reaction mass down here, 100 tons about 300 feet over there, and I had 10 tons over here. And the shots, you were usually way off range. You're way in a bunker like 800 feet away underground during the shot, so everyone was safe. This is a scramjet. We did this work for the Air Force back in, I think it was 94 through 96. And I was sort of scolded by the head of the National Aerospace Plane Program because we actually did flight testing with scramjets at Mach 9. And they spent $2 billion and did not do a single flight test. Not a single one. We got things to turn on at Mach 9. We basically embarrassed them. But they got a lot of dinero out of that, a lot of cash. This is a scramjet traveling in Mach 9 downrange. So we had a 100-foot range out here, maybe 150 feet, and there was sandbags in that target area there. This is a daytime shot, but the thing was traveling so fast, everything else looks dark because the cameras were high-speed cameras. Self-illuminating, basically. And this is a little, I wanted to understand a little history of space, so I phoned up on it by looking at Wikipedia. And you guys probably recognize these people. Tsiolkovsky was the rocket guy, right? The Russian physics teacher. Then you have Wernher von Braun, the slave master. Really a nice guy. Yuri Gagarin, first guy to actually orbit, right? And of course that got us ticked off, and so we planted the flag about, what, I guess 8 years later on the moon. When I was a little, I would think I was a 12 or 15-year-old kid at the time. I was fishing in Idaho when that happened. It was great. And these are the guys who popularized gun launch to space. And of course, Isaac Newton had a, when he invented calculus, he was able to figure out that if you were perched on a hill with no air, you shot a gun horizontally at 8 kilometers per second, would come back in a circle. So he's the first guy to figure that out. And then of course, Jules Verne, Eric and I were recently interviewed by this, who was that? Prophets of Science Fiction.
Discovery Channel.
Yeah, Discovery Channel on this topic because, of course, he was the granddaddy of science fiction, and he wrote a book called The Earth to the Moon. And then, of course, Heinlein was one of my favorites, and he was looking at using a pulsed induction gun to launch rocks at the Earth. Sort of interesting. And of course, Gerard O'Neill was a particle physicist, like I had been when I was a kid. And he invented, I think, the synchrotron storage ring, but then he went ahead and did the mass driver, the L5 colonies, and all that kind of stuff. So a little bit of stuff there. So our first phase, one goal, is basically we want to launch a very vanilla payload and just break the world altitude record. This would be done at White Sands. And the world record set by this guy, Gerald Bull, back in 1966, what was called the Y-28 shot. So we get to 200 kilometers pretty rapidly because he was using gunpowder. And we'll get that probably about shot 10. And we'll do a 20 shot sequence, basically. Hopefully get it by the middle shot. Okay. So now, Eric was the guy who brought up the fact that we not only could use hydrogen gas guns on the Earth, but once we get to Mars and set up an infrastructure, we can use them on Mars, because Mars is in a better place in the gravity wells of the universe in order to distribute stuff to different places and to augment exploration. So that's why my designer whipped up this picture here, which is representing the red planet, showing one of our orbiting propellant depots around it. So, and it turns out, if Mike can show you this stuff, it turns out it's much easier to launch at 3.6 kilometers per second from Mars at a 10-degree launch angle, because you have very little atmosphere, than it is to launch at 6 kilometers per second at, say, 25 degrees from an aquatic system or one on ADAC. It's actually much easier. Now, the hook is, you've got to get to Mars and set up the infrastructure first. So this is not going to come easy. It's going to come later on. Once the infrastructure is in place, that curve I showed you, the amortization curve, will dominate. It will show you that that's actually a better way to put stuff off of Mars if it's rugged. Okay, if it's ruggedizable like propellant, it's a better way to put propellant in space than if you used rockets. Okay, so summary. Hydrogen gas gun velocities are ideal. They're perfectly suited for delivering propellant because orbital speeds are commensurate with hydrogen gas gun speeds. And the second, of course, is that 90% plus of the mass you need is propellant for these exploration missions. And I think that's really where the action is. I mean, I share feelings with you guys that NASA's had 40 years to do show and tell in LEO, but they should have been going on and doing something beyond that. We need to do exploration. And so rockets plus quick launchers will revitalize manned space exploration this century. That's our belief. Let's see, there's a little picture. Let's see if I have anything else, but that's probably it. Okay, I've got some other curves, but any questions? Yes, sir.
You're mentioning you're recovering the hydrogen. Now, I understand there's two kinds. There's a thing called a light gas gun, which is meaning a light gas like hydrogen, where the gas is just injected into the gun without combusting with oxygen.
No, that's what we're doing. We're not actually combusting. This is a light gas gun.
Okay, but you were comparing it to gunpowder or something, as if you're actually combusting the hydrogen in a propagation way with the oxygen mixed inside the gun. And I wasn't quite sure which way you're doing.
No, this is a conventional light gas gun. There's nothing special about it.
So you're just injecting the hydrogen in all the way along the gun, or?
No, I've actually done analysis on sequential injection along a gun.
Yeah.
And it's more complicated than you want to work with.
Right.
So we like the breech injection. We're going to heat the hydrogen up. Now with Super Harp, the one we ran back in the 90s, we used a giant piston. It was about this big, it weighed a metric ton. And I would slam it in there 340 meters per second into this column of hydrogen. So it was traveling down the pump tube going essentially Mach 1 in compressing the hydrogen in front of it. That's how we conditioned the hydrogen. So the hydrogen was going from, say, 60 psi to 6,000 psi, like that. Temperature was rising to 1,500 Kelvin, like that. So we had the perfect mix, but there was no combustion going on there at all.
So when the thing comes out of the end of the gun,
Yes.
and you have a gout of hydrogen coming out,
Sure do.
that's really hot, it doesn't instantly catch fire and burn
Oh,
in
no,
the
it does.
oxygen?
It does unless you capture it. In fact, I have videotapes, if I could only show them here. Maybe we'll do it later on, but we have videotapes showing these shots, and they're spectacular shots. But in fact, since hydrogen costs a little bit, it's nowhere near like helium, but hydrogen costs a little bit, you want to recycle it.
Yeah.
So naturally, I built a silencer for this thing, not for super hard, but for a smaller system, a 10-foot system. Bam, worked like a charm. It's easy to build a silencer when it just captures all the hydrogen. We capture it, we scrub it, we put it back in the tank, and get ready for the next shot.
And of course, the hydrogen, as it burns, isn't very bright because there's no carbon.
Right.
to
Well, that's what
glow
everyone
inside.
told me, but I saw the shots.
Yeah.
Yeah. That's a theory, but it's not true. Okay? I mean, I'm with you.
But
I used to be a theoretical guy also.
But you'd be getting plasma glow from the passage of the object through the air anyways.
Well, let's put it this way: it's going so fast.
Yeah.
You can't. We were looking on TV monitors actually, except for people on an observation platform 1,000 feet away. Yes, sir. Yeah.
Okay. Another quick question for the water-based one: how stiff does it have to be? Because you're going to have different depths, you're going to have different currents.
You bet.
And so that's going to inform your.
It can. I did the math on some of those possibilities. It looks like the currents, number one, are pretty much global. So in other words, you're going to have like a 1/10 of a meter per second drift locally in this one patch of ocean, but it's like 5 kilometers wide. So the differential is what would kill you if it was
You
huge.
inversion layers, so you're going to have, you could have different currents at different depths.
Oh, no doubt. Yeah, you'll have basically wind shear. You can have wind shear in the ocean, but it's not very sizable. I've looked at the numbers. You do have, of course, a thermocline, so temperatures drop when you get to 500 meters, which the bottom of that system is 500 meters. But there's a whole spectrum of sizes of these systems. The first one I want to do commercially launches 100-pound payloads. The one in Popular Science was talking 1,000 pounds. But that would be a final system, which you don't even necessarily need.
When you say 100-pound payload, is that 100 pounds of fuel delivered to orbit? Is that 100 pounds
No.
going in the gun?
The former, yeah. It's the true payload. Yeah. Yeah. Yes, sir.
How much velocity do you lose by the time you leave the atmosphere?
You lose about half a click per second. Yeah, you come out at 6, you lose about half a click, so you're 5.5. Gravity scrubs something off, and you start when you get to about 490 kilometers. You turn the motor on and burn for about a minute. You start to rise at 500.
Last question.
Yes. I'll do both. I'll do quantum mechanics. Both you guys simultaneously, okay?
The question is, do you evacuate the barrel?
Yes, sir.
before-
5 torque. And then what happens is it blows out the mylar diaphragm, so the vehicle goes through unscathed, but you don't want to push all the air in front of you because it's parasitic mass. Absolutely. 5 torque. What was your question? I'll give you a nanosecond answer.
How long your burn is, how much methane you burn?
Burn for half an hour. A lot of methane. And I don't have the numbers in front of me, but it's a lot of methane, yeah. But basically, when you compare it to rocket numbers, it's actually less. Okay. These are not small systems that I work on, so it's a significant amount of methane. But it's cheaper than any rocket equivalent. Yeah.